Hey y'all, welcome back. Tonight we are reviewing for our Unit 4 test, which covers all things derivatives. We went over implicit differentiation. We approximated values using tangent lines. We were introduced to some new transcendental derivatives, notably the inverse, sine, cosine, tangent, all those inverse trig functions. We also went over how to differentiate exponential functions and logarithmic functions and inverse functions. And then finally, we also learned about L'Hopital's rule, which is going to help us evaluate limits. And finally, we talked a little bit about differentiability. And so let's go ahead and get started here. Number one is asking for us to find the derivative of y prime. And so on some of these, we'll have to differentiate implicitly. Some of them we will not. So when you differentiate implicitly, basically what I'm talking about there is that if you have got an equation where the y is not isolated, that's when you're going to be differentiating implicitly. So let's just go ahead and start with A. We're trying to find y prime. So I'm going to differentiate both the left and the right-hand side. So I'm going to take the derivative of both of these sides. So the derivative of the left-hand side with respect to x is going to be 3x squared. And then I'm going to have to use product rule on this second term, where the first factor is 2x and the second factor is y. So derivative of 2x is just 2. So 2 times y plus, and then I'll have 2x times the derivative of y, which is that dy dx or y prime. And that y prime is what we're going to eventually end up solving for. So as we go through it, this term right here, this is what we want to isolate. So let's keep going. Plus 6y, and then using the chain rule, we got to multiply that by y prime, and then the derivative of any constant is just 0. So what we're trying to solve for here is that y prime. So we're going to try to isolate that by moving the terms 3x squared and 2y. So this whole expression here, we're going to move over to the right-hand side, and then we will factor out the y prime as a GCF and then divide. Those are kind of the steps for the implicit differentiation. So we'll start by moving the 3x squared plus 2y over to the right, and that'll give me 2x y prime plus 6y y prime equals negative 3x squared minus 2y. And then I'm going to factor out that y prime, which is what I'm trying to solve for here. All right, this is y prime right here. So I'm going to factor that out like a GCF, using the distributive property in reverse here, leaving me with 2x plus 6y in parentheses. And then to get that y prime isolated, I need to divide both sides by that expression in the parentheses there. So I get negative 3x squared minus 2y over 2x plus 6y. Letter B, I do not have to do any implicit differentiation because y is already isolated. So when I differentiate both sides, I'm going to have the y prime by itself right off the bat here. So yeah, I'm going to have y prime equals, and then I will have to use product rule with my two factors being 5x and arc cosine of x cubed. Now you do need to know all the inverse trig derivatives. So inverse cosine, if I want to differentiate that, just a little reminder, is going to be negative 1 over the square root of 1 minus x squared. And so when I differentiate that piece, we'll kind of get to that. But so anyway, the derivative of 5x is going to be 5. So 5 times arc cosine of x cubed plus, because I'm using the product rule here, 5x times the derivative of arc cosine x cubed. So be careful here. The x cubed, I'm going to have to use chain rule here. This x cubed is going to be like where the original x was, right? But then I will have to multiply by the derivative of x cubed, which, as you should know, is 3x squared. So the derivative of arc cosine of x cubed is going to be negative 1 times 3x squared, or here, I'll write it separately. So negative 1 over square root of 1 minus x cubed squared times the derivative of x cubed, which is 3x squared. So you can actually leave it like this, and that's fine. Although if you might want to be prepared if there is if it's multiple choice to go ahead and kind of pull that second term together and write it as, let's see, 5 times 3 would be 15, or I guess the whole thing would be negative here, negative 15x cubed over that square root of 1 minus x to the, let's see, 3 times 2 would be 6. So either way is fine. Yeah, so anyway, that would be your answer there. I think I'm going to leave that initial one boxed rather than the one I have below. Okay, part C, another product rule here. We're going to have to use product rule and chain rule. Okay, so here are my two factors. So I'm going to start by differentiating the first piece. So here's another new derivative. So the derivative of an exponential here, like if I want to differentiate, use a different color here so this doesn't get all mixed up. So if I want to differentiate a to the x, I'm going to get a to the x times the natural log of whatever that base is, a. Okay. So yeah, the derivative of 3 to the sine x would be 3 to the sine x times the natural log of 3. But then I've got to use chain rule here. So I'm going to multiply by the derivative of sine, which is cosine. Okay, times secant of 5x. So that is all from the first part. Let me drag it over here because we are definitely going to need a little bit more room here. I'll just go ahead and write y prime. Okay, so that's just the first piece, right? This is the, right here, that's the sort of like your f prime, and here's your g, right, of the first part of that product rule. So plus 3 to the sine x. I'm going to leave that alone. Now I need to differentiate secant of 5x. So this is an older one. The derivative of secant is secant times tangent. So this is going to be times secant of 5x times tangent of 5x. And I do have to use chain rule times the derivative of 5x, which is 5. And yeah, wow. Okay, that is a long answer there. I don't even think I can move that over anymore. Okay, so D is going to be another instance of where we have to use the implicit differentiation. Notice we've got a couple of different y's in there. So just remember, when we differentiate an expression with y, got to use the chain rule, and the derivative of y is going to be your dy dx, or in this case, y prime. So the derivative of e to the y is just going to be e to the y times the derivative of y, which is y prime, plus derivative of 2x is 2. The derivative of 5 sine x is going to be 5 cosine x. And the derivative of 3y is going to be 3 times y prime. So trying to isolate y, we need to move all of the terms here that don't have a y prime, or that do have a y prime. We're going to move those to the left. And then these two terms that do not have a y prime we'll send over to the right. So e to the y times y prime minus 3y prime equals 5 cosine x minus 2. And now I've got those y primes all over to the left here, and so I can factor it out like a GCF. So y prime times e to the y minus 3 will equal 5 cosine x minus 2. And if I divide both sides by e to the y minus 3, I'm going to get y prime equals 5 cosine x minus 2 over e to the y minus 3. Okay, so there's a little sampling of the differentiation that you're going to be expected to know how to do. You're going to need to know all those inverse trig derivatives. You're going to need to know exponential and logarithmic derivatives, and chain rule is going to be a common theme here. Just make sure that you know all those. Yeah, and brush up on that product rule too, especially when you get kind of a crazy long one like we got in C. All right, number 2, we're evaluating limits, and I'm going to try to use L'Hopital's rule whenever I can, even though back in Unit 1 we learned other algebraic techniques like factoring and canceling. We learned about multiplying by the conjugate. So there's a few algebraic techniques that you could use on some of these, but I'm going to try to use L'Hopital's rule when I can, because those there will be some problems where you just don't have any algebraic techniques to work from. So let's start with A. Notice if I try to plug in 2 here, I'm going to get 0 on top, 0 on the bottom. So that's how I know I'm going to use L'Hopital's rule. So I'm going to differentiate both the top and the bottom here. The derivative of the top is going to be 2x minus 1. The derivative of the bottom is just 1. And now I have no problem doing direct substitution. Plugging in 2 is going to be 2 times 2 minus 1, which is 3. Part B. X is going to infinity here, so this is where we're going to check whether it's going to positive infinity or negative infinity. And as I plug in some large positive number, it doesn't even have to be that big, we're going to get a positive over a positive. So we have a little bit of an issue here, right? Like we know it's growing. Oh, wait a minute. This is growing faster in the denominator. So we don't even have to check. This is not going to positive or negative infinity. What am I talking about? Since all polynomial functions grow faster than all logarithmics, it's going to be bigger on bottom. The bottom grows faster. Okay, and anytime that happens, an infinite limit like this is going to go to 0. Okay, so just to kind of review here, all exponential functions are going to grow faster than all polynomials, and all polynomials will grow faster than all logarithms. And that's if x is going to infinity. If x is going to negative infinity, we're going to have to, we'll cross that bridge when we get there. Okay, so C, we've got cosine of x over x. In this case, x on the bottom is growing faster again. The bottom grows faster. The top is not even growing at all. It's periodic, or it oscillates is another way to put it. So the value of the numerator is just going to kind of bounce in between 1 and negative 1. It's not growing at all. But the denominator is growing much faster. So we've got a small number over a larger number. This is going to equal 0. Okay. So I suppose sine or cosine, that would be like the slowest ones. Sine or cosine. Okay. So maybe I'll put, let's see. So I'll just put, sine cosine. D is another infinite limit. Notice that the denominator is growing faster again because we have that exponent of 2. So the degree on bottom is bigger. So we do have a horizontal asymptote at y equals 0. The bottom is growing faster again. So this is just going to equal 0. For E, same kind of deal here. We're going to infinity, so we're going to check what's growing faster. Exponentials grow faster than polynomials. So kind of getting annoying here, but yeah, the bottom's growing faster. So this is going to equal 0. Okay, F. This is going to be a little trickier. If I try to substitute 0 in here, this is not an infinite limit, right? X is not going to infinity. If I try to substitute 0, I'm going to get 1 minus 1, which is 0 on top, and then sine of 0 is also 0. So I get 0 over 0, so this is where I want to use L'Hopital's rule. The limit as x approaches 0 of e to the 4x times the derivative of 4x, which is 4, over cosine of 2x times the derivative of 2x, which is 2. Okay, now I think I'll be safe here plugging in 0, but if not, I could use L'Hopital's rule again, but let's just try. So plugging in 0 to the numerator, I'm going to get e to the 0, which is 1. 1 times 4 is 4. And plugging it into the denominator, 0 times 2 is 0. Cosine of 0 is 1, and 1 times 2 is 2. So we get 4 divided by 2, which equals 2. Number 3, selected values of the function and its derivative are shown. If g is the inverse, and on the AP test, they'll actually be more specific about this just to make sure that you understand that this is not being raised to the negative first power. Okay, this is the inverse of h. What is the value of the derivative of that inverse? Okay, so the derivative of g here, which is the inverse of h, will be 1 over the derivative of h of g of x, where g is that inverse. So if we want to evaluate g prime at 7, that's going to be 1 over h prime of g of 7. Now, g is the inverse of h. Okay, so you don't see any g values in the table here, so it might be helpful to make a little table for x and g. And we're just going to take these values and reverse the inputs and outputs. So instead of there being a point 3, 7, we're going to have a point 7, 3. Instead of there being a point 722, we'll have 22, 7. So g of 7 is 3. So this is going to equal 1 over h prime of 3. Now, h prime of 3 is given in the original table, and it equals 5. So this will equal 1/5. Oh yeah, this is actually a multiple choice question. I just totally looked over that. Yeah, C. Number 4, for what value of x would this be true? Okay, so this looks like a complicated limit question, but really this is a derivative question. This limit is written in the form of the limit definition of the derivative. So this whole thing right here equals the derivative of this function right here. So it's the derivative of arctangent of x. So we want to find the derivative of that. So the derivative of arctangent of x, this is one of those that you just need to know, is 1 over 1 plus x squared. You want to know when is that 1 over 10. I think the easiest way to start this problem off, you could use cross multiplication, but if both numerators are 1, I just like to reciprocate both sides, and so 1 plus x squared is going to be 10. Subtracting 1 on both sides gives me x squared equals 9. I guess I should maybe move this over so I have a little bit more room. And so x would be plus or minus 3. Now we don't see plus or minus 3 here, and that's okay. It's just saying for what value of x could it be true, and so the only possible answer here is 3. Number 5, the velocity is given to determine the acceleration. Okay, so we talked about this in class, and I'm going to be a little bit more strict about this because on the scoring guidelines for the 2024 AP test, we saw that you could only get this point, or there was a question about the acceleration and velocity, and there was a question where you have to establish that the acceleration is the derivative of velocity. Now you might already know that, and so you might just kind of not even mention it, but you cannot take that for granted. We need to say that that the acceleration is equal to the derivative of the velocity. It's just a real short statement, but if you don't write that, then you're likely to lose out on a point that you really should get. So if we know that the acceleration is the derivative of the velocity, we can go ahead and differentiate this natural log function. It'll be 1 over t cubed minus 2t plus 12, but then times the derivative of the denominator. And we've seen a bunch of these natural logs where it's like 1 over something times the derivative. And when you multiply that derivative, it just ends up in the numerator. So I'm going to go ahead and just stick that in the numerator up front. So 3t squared minus 2 should be in the numerator. Now, if I want to evaluate that when t is 3, I'm going to evaluate a of 3, which is going to be 3 times 3 squared minus 2 over 3 cubed minus 2 times 3 plus 12. So 3 times 9 is going to be 27 minus 2 is 25. And then on the denominator, we've got 9 minus 6. So 3 plus 12 is 15. Hold up. Oh, wait. That's 3 cubed. Sorry, that's not 3 squared, so not 9. But 27 minus 6, that would be 21 plus 12 is actually going to be 33. Now, be ready to give some units here. This one doesn't actually have any units, so I would be fine with you just leaving it like this. But if it's looking for the units, let's say, if it was like meters and seconds, this would be like meters per second squared. If it was like feet per mile squared, or whatever the units are, it would look something like that. But this doesn't have any units, so we're just going to leave it as a fraction. Number 6. For a certain function f, we know that f of 4 is 1, and we know the derivative. So part A is asking for the tangent line at x equals 4. Okay, so write a tangent line. Back to this again. We need a point, right? And we need a slope. Okay, this is saying when x is 4. So x is 4, y is 1. Okay, we got our point. And the slope, what we need to do is figure out what the value of the derivative is when x is 4. So f prime of 4, since we already have the formula for f prime, we can just plug that in. 4 squared plus 5 over 4 plus 3 is going to be, 16 plus 5, that's 21. Over 4 plus 3 is 7. 21 divided by 7 is 3. So my slope is 3. So my equation is going to be y minus 1 equals 3 times x minus 4. B, use your tangent line from part A to approximate the value of f of 4.7. So we're just going to substitute this 4.7 into x and solve for y. So y minus 1 equals 3 times 4.7 minus 4. Y minus 1 equals 3 times 0.7. Okay, 3 times 0.7 is 2.1. So we've got 2.1, and then plus 1 is going to be 3.1. So we're going to say it's don't really want to say equal here. We're going to say approximately because we are approximating. Don't think I'll be like super picky about that, but if we're going to be technically accurate here, this is an approximation. So y is approximately 3.1. Part C is asking if the approximation is an over-approximation, is it greater than the actual value or less than the actual value? Now, we do not have the original function. So at this point in our calculus journey, we cannot just plug in 4.7 anywhere. So kind of a bummer. But what we can do is realize that if this line lies on a point of the curve where it's concave down, right, where the second derivative is negative, then it's going to be an overestimate, in which case the estimated value would be greater. But if this is on a point where we're concave up, then the tangent line is going to be below it, and so it'll be an under approximation, or the estimated value be less than the actual value. This is going to happen when the second derivative is positive. So basically what we need to do is figure out whether or not the second derivative is positive or negative when x is 4. So let's go ahead and erase all this. So let's find that second derivative. Okay, we know the first derivative, right? So the second derivative, we'll look back up here at the first derivative. we're going to have to use quotient rule to find that second derivative. Okay, so derivative of the top, 2x, okay, times the bottom is x plus 3, minus the top, x squared plus 5, times the derivative of the bottom, which is just 1. So I'm not even going to bother writing 1. Or maybe I should, just to keep track, make sure I did that. Divided by the bottom squared. So divided by x plus 3 squared. Okay, so we're going to find out, we're going to use the x value where the actual tangent line's hitting to determine at that point, is it concave up or concave down. So we're going to check the second derivative at x equals 4. So 2 times 4 is going to be, 2 times 4 is going to be 8. 4 plus 3 is 7, so 8 times 7, minus 4 squared is 16. 16 plus 5 is 21. And then the denominator, 4 plus 3 is 7, so it's going to be 7 squared. Now, we don't really care exactly what this equals. We're just interested in whether or not this is going to be concave up or concave down. 56 minus 21 is going to be positive. 7 squared is going to be positive. So this whole thing is going to be positive. Okay, so let's, we also want to justify our answer. Let's make sure we say everything we need to say here. So the approximation which is 3.1, is less than the actual value of f of 4.7. Now, how do we know that, right? What's our justification? We know that, or let's just continue this, because the second derivative at 4 is positive, so f of x is concave up. Okay, now again, let's think about that visual. Concave up, the line's below it. Okay, that's why the approximation is less than the actual value. So if we're approximating like here, you can see that the point on the line is below the actual point. Yeah, so that's basically it. So our answer is that it's less than the actual value, and the reason is because at the point where the tangent line is, the function is concave up. Okay. Yeah, so that's our answer there. Make sure you have that justification in there. Number 7. Looks like we're just finding another derivative here. So f prime is, you got to know your arc sine. So maybe I'll just write it over here. If you got arc sine of x, you want to differentiate that. A little reminder here, arc sine of x, the derivative is 1 over the square root of 1 minus x squared. So yeah, here we're going to have to use chain rule, but just to start us off, f prime x is going to be 1 over the square root of 1 minus, and let's be careful here, e to the 2x squared times the derivative of e to the 2x. So the derivative of e to the 2x is, well, e to the 2x times 2. Now, none of the answer choices look exactly like that, but whenever you have like one of these arc trig functions, arc sine, arc cosine, or arc tangent, but also if you're dealing with like natural log or the logarithmic one where your derivative is going to be like 1 over something, and then using the chain rule, that stuff that you're multiplying, just put that on top, because 1 times all that stuff is just going to be all that stuff. So f prime x is going to be 2 e to the 2x divided by the square root of 1 minus, and then when you raise a power to a power, you multiply your powers. 2x times 2 is going to be 4x, so e to the 4x. So that is our answer. And there should be, let's see here, either 2x. Looking good, looking good. Looks like our answer is D. Number 8, write the equation of the line, tangent to the graph, where x is 1. Okay, so another tangent line problem. We know how to set this up. We will need a point, which is going to be 1 comma something, and we're going to need a slope. And to find that slope, we're going to have to find the derivative, and we're going to have to use implicit differentiation to find that derivative. In other words, we're looking for y prime, or dy dx. So I already worked out a few implicit differentiations with y prime. I'm going to use dy dx here just so that I can be flexible and in which notation I'm going to use. So either way, the derivative on both sides here is going to be 2x. Now be careful with the minus. Okay, it's minus this whole term. So when we use the product rule, we're going to have to subtract both of the terms that we get from the product rule. So minus 3 times y minus 3x times dy dx. And the derivative of 13 is 0. Okay, really just to really clarify this whole minus business, if I were to do that over here, I'd have minus 3y plus 3x dy dx, and then go back and distribute this. But hopefully we've done enough of these subtracting a product problems to where you just kind of know that that's what's going to happen here. We can jump straight to the minus minus. All right, so just to clean this up, I'm going to erase that. Okay, so we're looking for the slope, which means we need that dy dx. We're going to solve for dy dx, and then we'll plug in the point, the xy point, so that we can actually calculate the slope. So solving for dy dx, we're going to isolate this. So we first need to move all these other terms to the right-hand side. It's going to be negative 3x dy dx equals 3y minus 2x. And then dividing both sides by negative 3x is going to give us our slope equation, 3y minus 2x over negative 3x. Okay, so now we need to plug in our point. Okay, we got the x, but I forgot to find the y. I should have found that up front, although that's okay if you find it second, that's fine. But at this point, we're going to need it. So I'm going to just kind of stick this over here for now. Let's go back and find that y value. So x is 1, so we have 1 squared minus 3 times 1 times y equals 13. So 1 squared is 1. 3 times 1 is 3, so 3y equals 13. Negative 3y equals 13 minus 1 is 12, so y is going to be negative 4. So that's going to be the y coordinate of my point, and now I can find the slope. I'm going to plug in 1 comma negative 4 into, back over here, the slope equation. So let's see here. So dy dx, so that slope at the point 1, negative 4 is going to equal 3 times negative 4 minus 2 times 1 over negative 3 times 1. So that'd be negative 12 minus 2 is negative 14 over negative 3. So the slope is going to reduce or simplify to be 14 thirds. And now that we have the point and the slope, we can go ahead and write our equation here. Y plus 4 equals 14 thirds times x minus 1. Number 9, the third derivative of a function f is continuous on the interval 0 to 4. Values for f and the first 3 derivatives at x equals 2 are given to the table below. What is this limit? So I'm kind of guessing this is going to have to be a L'Hopital's rule question, but let's just check. If I plug in 2, f of 2 is 0, and then 2 minus 2 is 0. So yeah, we're going to have to use L'Hopital's rule here. So the limit, this is going to equal the limit as x approaches 2 of the derivative of f, and then we'll use chain rule here, 2 times x minus 2 times the derivative of x minus 2, which is just 1, so I really don't have to worry about it too much. Now I'm going to try to plug in 2 and see if it works, although I'm guessing that we're going to have to use it again. Otherwise, why would they give us the third derivative? So yeah, plugging in 2, I'm going to get 0 over 0 again. So bummer. Now I'm going to actually rewrite this to make the differentiation a little easier. The denominator I'm going to write is 2x minus 4. So this is going to equal the limit as x approaches 2. Using L'Hopital's rule again, we're going to have the second derivative over, just 2 here. So the second derivative at 2 is going to be 5. And so this is just going to equal 5 over 2. And so our answer is B. Number 10, we've got a piecewise function with a potential point of discontinuity at 3. And part of the goal here is to figure out whether or not it's continuous and whether or not it's differentiable. So the first part is asking, does this point actually exist? Okay, well, if I substitute 3, no, I'm sorry, it doesn't ask whether or not the point exists. It's asking if the limit exists. So we need to know if the left-hand limit equals the right-hand limit. So to answer this question, we need to know, does x plus 2 equal, we don't know, 4x minus 7 when x is 3? So we'll evaluate both of these separately. Now, if the limit exists there and it equals the value of the function, which we'll check anyway, then we can also say it's continuous. So this little check here of if these two values are the same, if they are, then we're going to be able to say that both 1 and 2 are true. So let's check. 3 plus 2 is 5. Okay. 4 times 3 plus 2 is going to be 12. Sorry, it's not plus 2. Minus 7. It's I don't think that's right. Minus 7. So 12 minus 7 is 5, right? So now we can say that the limit exists. Okay, so this is true. It's continuous because the value of the limit here is 5, and that also is the value of the function, because if I plug in 3 here, I get 5. So we know the limit exists, it's continuous. Now we just need to know if it's differentiable. And in order for it to be differentiable, we need to check if the derivatives are the same at x equals 3. So the derivative of the first one, so this is what we're going to check. We're going to check, is this the same as the derivative of 4x minus 7 when x is 3? That's what we're checking. So let's first find the derivative of each side. The derivative of x plus 2 is 1. The derivative of 4x minus 7 is 4. Okay, these are not equal. So that means, nope, it's not differentiable, so our answer is D. Number 11. It says determine the derivative of f, given that f is this. So we're really just finding the derivative here. So f prime is going to be 1 over 3x squared plus 6, that whole thing times the natural log of the base, which is 5. That's where I'm getting the 5 from, is right there. Times the derivative of 3x squared plus 6. So that's going to be times 6x. So putting it all together, and I really like putting this on the numerator just because it just looks so much better without without having an extra multiplication there. 6x over 3x squared plus 6 times the natural log of 5. Number 12. Let f be a function that's differentiable for all real numbers. The table of values of f and its derivative for selected points are given. Write the equation of the line tangent. Okay, so write the equation of the line. Again, every time I see that, I'm just going to get my whole thing set up here. I need a point and I need a slope. At the point where x is -1. So where x is -1 is going to be right here. The y value is going to be -4. So my point is -1 comma -4. I need to find my slope. And hey, look at that. It's given right here. Okay, slope is -5. So my equation of my tangent line is going to be y plus 4 equals -5 times x plus 1. So I've satisfied that part of the question, and then it says use that line to approximate the value of f of -1.2. So we just need to substitute that in for x. We don't have any information about the second derivative, so we won't be able to say if it's an over or under estimate. We won't be able to check concavity, unfortunately, but no big deal. So so we're going to substitute in, negative 1.2 into x. So y plus 4 equals negative 5 times negative 1.2 plus 1. Negative 1.2 plus 1 is going to be negative 0.2. So we get y plus 4 equals negative 5 times negative 0.2. See, 5 times 2 is 10. So that means negative 5 times negative 0.2 is just 1. Y plus 4 is 1. And if I subtract 4 from both sides, I'm going to get y is approximately negative 3. So really, like what I want to say here, I guess, if I'm trying to be precise here, f of negative 1.2 we'll say is approximately negative 3. Number 13. We've got a function for f, and we've got a point on f. Determine the value of the derivative of the inverse of f at x equals negative 5. Okay, so the inverse, let's just go over this again. The inverse of f at x, if we want to differentiate that, that's going to be 1 over the derivative of f inverse of x. Now, a lot of times we'll just write the inverse as g, and if that's easier, I would say just go for it. But I'm going to leave it like this for now. Okay, so let's figure out what we're trying to solve for here. So if f of 2 is negative 5, that means f inverse of negative 5 is 2. So I'm going to make a little point there. And that's what we're actually trying to find, where x is negative 5. So if we want to evaluate f inverse at negative 5, find that derivative. Hold up, am I writing that right? Yeah, I think so. Well, no, actually, I'm. So anyway, we want to evaluate this when x is negative 5. So I'm going to write 1 over f prime of f inverse at negative 5. Now we know the f inverse at negative 5 is 2. So this is going to equal 1 over f prime of 2. I never wrote that. Sorry, I got sidetracked here. F inverse of negative 5. There we go. Okay, so this is going to be 1 over f prime of 2. And f prime of 2, well, we need to evaluate that. We have f, but we don't have f prime here. F prime of x is going to be 6x squared minus 9. So if I plug in 2 there, f prime of 2 is going to be 6 times 4 minus 9. 6 times 4 is 24. 24 minus 9 is 15. Minus 9. 15 and 9 is 24. Sorry. So that should be 15. So it's going to equal 15. So that's going to be 1 over 15. Number 14 says determine the points on the curve where there are horizontal tangent lines. Okay. So horizontal tangent lines, that means that dy dx or y prime, whichever one you want to say, is 0. And so what we need to do is we're going to find that dy dx, set it equal to 0, and then solve for x. So let's start with the actual derivative here. So we've got 2y times dy dx minus 2x plus 8 equals 0. So if I isolate that dy dx, 2y dy dx will equal 2x minus 8. Dividing both sides by 2y is going to give me my actual derivative here, which is 2x minus 8 over 2y. Okay, so if I'm looking for these horizontal tangent lines, they will be whenever this thing equals 0. Okay, now if this is going to equal 0, if 2x minus 8 over 2y, if that equals 0 and I multiply both sides by 2y, that's going to simplify to just 2x minus 8 equals 0. Adding 8 to both sides gives me 2x equals 8. And dividing both sides by 2 is going to give me x equals 4. So I do need ordered pairs. I got the x value where that horizontal tangent line is. So it's going to be 4 comma something. But I'm going to go back and actually solve the original equation to find out what that y value is. Let's move this over a little bit. Going to separate out what we're doing here. Okay, so now I have my x, so I have y squared minus 4 squared plus 8x equals 20. Oh, and x is 4, so let's fix that. 8 times 4 equals 20 there. So y squared minus 16 plus 8 times 2 is 16 times 2 is 32 equals 20. 32 minus 16 is 16. So this should be y squared plus 16 equals 20. Subtract 16 on both sides, I get y squared equals 4. So y could actually be plus or minus 2. So we actually have two coordinates here, 4 comma 2 and 4 comma negative 2. So you can write them separate like that, or you could just write it as 4 comma plus or minus 2, and that'd be acceptable as well. But there are two coordinates there. Number 15. So we're going to let G be the inverse of f. So G is the inverse of f. Use the table of values to write the equation of the line tangent to G at x equals 5. Another equation of the line tangent. So we're going to need a point. We're going to need a slope. So let's just get that template ready to go. At x equals 5, we can see that y is 1. So that's our point, 5 comma 1. Yeah, so the slope, well, we don't know the slope yet, do we? Oh, wait, hang on here. Hang on. Tangent to G, oh, at x equals 5. Oh, goodness. Okay, we need to back that up because we're not finding the point at f of x. We need g of x. So let's write g of x here. Whew, almost made a mistake there. So for g of x, let's make that table for g of x. So g is the inverse of f. So if there's a point 2 comma 4 on f, then g will have a point 4 comma 2. We'll also have a point 5 comma 3 and 1 comma 5. Yeah, almost made a big error there. So the point is actually going to be 5 comma 3. I'm going to use that point on G. That's the reason why I'm using G here is because I want to find the line tangent to G, not to F. All right, so let's go ahead and find our derivative here so that we can get the slope. So we're trying to find the slope when x is 3. So we've got g prime. I'm sorry, when x is 5. I said 3, kind of got ahead of myself there. 1 over f prime of g of 5 is going to be 1 over f prime. So g of 5 is 3. So f prime of 3 is 2. So this is going to be 1/2. So that's going to be our slope. And now we can write our equation, y minus 3 equals 1/2 times x minus 5. Number 16, the volume of a spherical hot air balloon expands as the air inside the balloon is heated. The radius of the balloon in feet is modeled by the function r, okay, so that's going to be this one, of time t, where t is measured in minutes. The table below gives selected values of the rate of change. So this is giving you the derivative of r. We do not know what the any values for r. But it does say that the radius of the balloon is 30 feet when t is 5. So one way to interpret that is that r of 5 is 30. Okay. It says estimate the radius of the balloon when t is 5.4 using a tangent line approximation at t equals 5. Be sure to show the equation of the line. Okay, so let's find that equation of the line. We need a point. We need a slope. Now we're not going to use x and y here. We're going to use t and r. So x and y are out. We're going to use t and r. So our point is going to be in that t comma r format. So when t is 5, we need to figure out what is r. Now we don't, we don't have a table for r, so we can't find it directly. But they did tell us r5 is 30. So what that means is that if t is 5, then the r is 30. So we got 5 comma 30 there. The slope is going to be the slope when t is 5. So that's given right here. It's 2. That's the slope. Now I can write my equation. I'm not going to use y and x. I'm going to use r and t. So r minus 30 equals 2 times t minus 5. And I'm going to use this equation. And if you write it, and by the way, if you just want to write it like this, like that's totally fine. Okay, if you're just like getting thrown off by the r's and t's. At the end of the day, we're just trying to find that approximation. But I'm going to leave it r's and t's, and hopefully you can kind of follow along here. We want to use this to approximate when t is 5.4. So we're going to substitute 5.4 into t. And so we get r minus 30 equals 2 times 5.4 minus 5. And I guess at this point, we'll just say approximately. So 5.4 minus 5 is going to be 0.4. So r minus 30 is approximately 2 times 0.4. 2 times 0.4 is going to be 0.8. So r minus 30 is approximately 0.8. Add 30 to both sides. So r is approximately 30.8 feet. Number 17, what is the value of the limit as x approaches 0? And if I just try to substitute 0 in here, I'm going to get 0 over 0. So I'm going to have to use L'Hopital's rule. So this is going to equal the limit as x approaches 0. Now with L'Hopital's rule, just remember, you can only use that if it's 0 over 0 or infinity over infinity. You can only use it when you have an indeterminate form. So you always try to plug in the number first, because sometimes you get lucky and you don't have to use any tricks. You just plug it in and get your answer. But here, if I plug in 0 here and here, I'm going to get 0 over 0. So that's no good. We're going to use a L'Hopital's rule. So e to the 2x, the derivative of that, is just e to the 2x times the derivative of 2x, which is 2, over the derivative of tangent. And hopefully you haven't forgotten that one yet. It's secant squared. And so now I'm going to try to plug in 0. Okay, now you might be a little concerned at this point because you might be wondering, oh, what is secant of 0? I don't know what that is. Well, hopefully, what you remember is that secant is the reciprocal of cosine. So if I try to plug in 0, I'm going to have e to the 0 times 2 times 0, 0, over 1 over cosine squared of 0. If you do it like this might make it a little bit easier for you to process here. E to the 0 is 1. 1 times 2 is 2. Cosine of 0 is 1. 1 divided by 1 is just 1. So 2 divided by 1 is 2. That one's a little tricky. Got to know a little something about secant. Know that secant is the reciprocal of cosine. So this is not going to happen very frequently where you have to evaluate one of the reciprocal trig functions, but you got to be prepared to do that. Number 18, we're looking for dy dx. This is just going to be a implicit differentiation problem. I'm going to rewrite the equation over here just to give myself a little bit more space to work. And so now I'm going to differentiate both sides. The derivative of 3x is 3. The derivative of tangent is secant squared, like we talked about before. So we have secant squared y times the derivative of y. So that's going to be times dy dx equals 0. So solving for dy dx, I'm going to subtract 3 from both sides. And then I want to divide negative secant squared y on both sides. So dy dx is going to equal negative 3 over negative secant squared. So I'm just going to, negative divided by a negative is just going to be positive. So positive 3 over secant squared y. Now notice none of the answers look like that. In fact, secant's not in any of the answers, but secant squared is the reciprocal of cosine. So this is going to be equal to 3 times cosine squared y. So this actually just happened back to back, right? Where you have to know that secant and cosine are reciprocals. So, there might be a little hint that, hey, maybe you should commit that to memory. So secant and cosine are reciprocals. Similarly, cosecant and sine are reciprocals, and tangent and cotangent are also reciprocals. So is our answer even here? Yeah, okay, it's B. All right, we just have a couple questions left here. This has been a pretty good review, I think. Try to keep these reviews, about the hour mark, and I think we're a little bit over there at this point. Not really keeping track of time, but hopefully it's not too bad. 19 says, look at the function below. If f is differentiable at x equals 2, what's the value of c plus d? This was a problem that I gave you on the little game we played the other day. So let's break this down a little bit. In order for it to be differentiable, not only do these two pieces have to be equal at x equals 2 to ensure it's continuous, but also the derivatives have got to be equal. So let's start with just setting these equal to each other to satisfy the continuity. So we have cx plus d equals x squared minus cx, but where x is equal to 2. So c times 2 plus d equals 2 squared minus c times 2. That's going to be 2c plus d equals 4 minus 2c. And so let's see, 2c plus 2c is going to be 4c plus d equals 4. So that's one little equation we can set up. The next equation we can set up is going to be based on the fact that the derivatives are going to have to be equal at x equals 2 in order for this to be differentiable. So the derivative of cx plus d is just c. And the derivative of x squared minus cx is going to be 2x, so 2 times 2 minus c. So if I add c to both sides, I'm going to get 2c equals 4. Divides 2 on both sides, gives me c equals 2. All right, so c is 2, but it's asking for c plus d, so I've got to actually find d also. So I'm going to put this 2, so I know that's what c is, right here, and then solve for d. So 4 times 2 plus d is 4. 4 times 2 is 8. 8 plus d is 4. So d is negative 4. Okay, so I got c. I got d. 2 plus negative 4 is going to be negative 2. So our answer here is B. All right, that takes us to our last problem, which has a couple little parts here, but these are just straight derivative problems. Hopefully there's enough chain rule here and enough of the new derivatives here, enough practice so that you can hopefully have all these committed to memory. But also go back and look at that guide that we created, that master list of all the derivatives, and you can use that to study as well. Just make sure you know them all. So yeah, number 20A is going to be, y prime is going to be 1 over x cubed plus 5 times the natural log of 4. All of that times the derivative of x cubed plus 5, which is 3x squared. So I'll just clean that up a little bit and write it as 3x squared over x cubed plus 5 times the natural log of 4. Make sure you put the x cubed plus 5 in parentheses, otherwise it's going to be wrong. 20b. Okay, so we got arc cosine x cubed. So my outside function is something cubed. So y prime is going to be 3 times the something, which is the arc cosine x squared, times the derivative of arc cosine. So that's going to be times this fraction of negative 1 over the square root of 1 minus x squared. So, you can actually leave it like that. You know how I am about simplifying. It's not that big deal if you simplify, but gosh, it just looks nice when you combine these fractions that have a 1 on top. Now, we do have a negative 1 on top, so this is going to be negative. So negative 3 times arc cosine x squared over the square root of 1 minus x squared. That should be about it. But if you left it like this, that's fine. I mean, same thing up here. If you leave it like that, I'm pretty happy. And finally, we got C, where we've got a product. So we're going to have to use product rule. We've got a little chain rule embedded in there on that first term because of the 3x. So let's knock this one out. So this is going to be another long one, I think, because of the exponential. So y prime is going to be let's start with the derivative of 4 to the x. This can't even read it. 4 to the power of 3x. So 4 to the power of 3x times the derivative of 3x, which is 3, times the natural log of 4. If you want, I kind of like actually putting the natural log next, because that is like the derivative of the 4 to the whatever, and then times, using the chain rule, the derivative of 3x is 3. The order here doesn't really matter because multiplication is commutative, so you can write it in any order, but I'm going to leave it like that. So that's just the derivative of 4 to the 3x times the inverse sine of x. And so that's just the first piece. Then we have plus the first thing, 4 to 3x, times the derivative of inverse sine x, which is 1 over the square root of 1 minus x squared. You guys know how I feel about those 1 over fractions, so I'm just going to rewrite everything the same. That is a lot of multiplications on that first term. Except I'm going to put the 4 to the 3x on top. You don't have to do this, but if it's a multiple choice question, it's most likely going to be written like that. Okay, that's it. As always, please reach out if you have any questions, and I'll be happy to help you. But otherwise, y'all have a great day, and I'll see you next time.